In this lecture series, we are trying to understand the basics of radar systems. Radar means radio detection and ranging. So it has got main two objectives. One is the detection and another is to measure the distance of the target from the radar. And the means by which it detects and measures the range is the radio wave. Now let us try to understand the history of this radar system. We can divide this history into two parts. One is pre-World War II and another is post-World War II. First, consider famous Hurge's experiment. During the year of nearly 1885 to 88, Hertz first demonstrated that we can transmit electromagnetic wave from one place to another place. Later on, number of scientists have developed transmitter and receiving system. In 1904, Halsmeyer demonstrated use for detecting ships in presence of fog. Unfortunately, at that time, nobody was interested with this kind of technology, because Halsmeyer said that that particular technology is very much suitable to avoid the collision between the ships. However, in 1922, US Naval Research Laboratory detected wooden ship on the other side of the river, and the research was carried out. Lot of research was carried out in 1925 using the similar kind of technology. Scientists measures the height of the ionospheres, and a lot of experiments was done. In 1930, NRA engineers detected an aircraft with simple radar system, because at that time aircraft becomes one of the major and important equipment for the battlefield or war. Now, just before World War II, lot of other inventions were done, but like people developed magnetron type of tubes that can generate huge amount of RF power in microwave region. But after and during World War II, army, mainly because of army, they have seen that it is one of the most important kind of equipment used for war. So a lot of development took place during Second World War, at the same time after Second World War, because after Second World War, excessive amount of research took place in antenna, microwave as well as electronics, and all the inventions helped the radar technology. So radar has deep military roots and it continues to be very important military equipment. At the same time, growing number of civil applications nowadays. So those are the background of this radar. Now we can try to understand the variety of radar applications just for examples. So if we have ground-based stationary monostatic radar. This is the type of radar. Monostatic means the transmitter and receiver are in the same geographic location. Now you divide this application into two categories. One is the civil application, another is the military application. So for this type of radar, we have different kind of civil application like weather radar, radar astronomy, traffic control, synthetic aperture radar, inverse synthetic aperture radar. And in military domain, we have air defense, missile defense, perimeter defense, something like that. Now, if we consider ground-based stationary but multi-static radar system, then the radar in civil application we have radar astronomy. In military application we have air defense like fencing type of thing, missile defense, etc. For ground probing type radar, we have archaeology, ice soundings, etc. For civil application. For military application, we have tunnel detection, landmine detection. This type of applications are available for military applications. Now, if the radar is placed in some flying object like airborne or spaceborne system, and if the radar is monostatic in nature, then we have some kind of collision avoidance altimeter. Altimeter is very essential for any sort of flying objects. Then imaging radar, synthetic aperture radar, which produces the image of the target. Then scatterometer. This type of applications are there. For military counterpart, we have search and track type of radar, fuzzing, imaging and targeting, navigation. This type of applications are there. And for airborne, spaceborne, multistatic radar system, for civil application we have interferometric synthetic aperture radar, then planetary exploration, etc. And for military application we have covert type of radar. This is an example of spaceborne imaging type of radar. So here radar is present, it transmits some pulses, and based on that it produces the image of the ground or whatever we want. We can map our entire earth with the help of this type of spaceborne imaging radar. Another example like fencing radar, the ballistic missile early warning system. So as you can see, there big antennas are there, and each antenna will cover huge geographic locations. That means if some missile comes from other part of the world, this whole system will warn the corresponding country long before the missile would, actually comes to the target. So this is a kind of fencing system. Another example is the weather radar. We have in India we have number of radars, spaceborne radars are available, and this type of radars gives us a lot of information about the cyclone, the rain, and all the weather, all the parameters related to weathers. We have some. This is taken from tropical rainfall measuring mission satellite data. For any location, we can determine the variation of rain rate. Actually, radar determines the reflectivity, and from reflectivity we can, using some model, we can generate corresponding rain rate. So it's a nice picture that shows the variation along with height. So here the amount of rain is higher, then we have some lowering of rain rate, then again some higher frame rate, etc. So this type of variation is possible to get with the help of radar. Another example of ground penetrating radar system. And this is the radar. So if you, here we have the transmitter and receiver system. So this is the radar signal path. So it determines, this is for the agricultural purpose, mapping of agricultural drainage pipes, etc. This is the mapping unmarked colonial era graves. So all these things are possible. This is the ground penetrating radar system. Now the characteristics of radar. First of all, it uses electromagnetic waves. Frequencies of the order of megahertz, gigahertz, terahertz. And the propagation is governed by the Maxwell's equation. Electromagnetic waves, actually light is also an electromagnetic wave, so it propagates at the speed of light in vacuum. Antennas or optics used to launch or receive the waves. Now the related technologies used acoustic waves like ultrasound, seismics, sonar. They are actually a kind of radar, but they are using some acoustic waves instead of electromagnetic waves. Now the active sensor. This radar is nothing but an active sensor. Why it is active sensor? Because it provides its own illumination. That means transmitter is present along with the radar system. Involves both a transmitter and receiver. Now related technologies are purely passive, and such examples are used in radio astronomy, radiometers. In radiometers, the principle is almost identical, that it receives the signal. Unfortunately, the signal is generated by the target itself. That means it is not illuminated by the radar. Concepts and technologies used in radar. Radars are systems involving a wide range of technologies and concepts like signal processing, antenna, electronics, communication, electromagnetic waves, etc. An understanding of radar requires knowledge over this broad range of technologies and concepts. As new technologies emerge and new concepts are developed, radar capabilities can grow and improve. Radar measurement capabilities. First of all, presence of target, which is called the detection. It measures the range of the target, that is distance as well as the direction. Received signal strength, that is useful for understanding of the target properties. Radial velocity with the help of Doppler frequency shift. Spatial distribution like mapping. Various target characteristics like particle size distribution. Example is the precipitation, surface roughness, water content of soil, snow, etc. Motion characteristics like aircraft engine rotation, rate, breathing of some living things. Surface displacement, subsidence. Example is the subsidence. Now we have different type of display. This type of display is the plan position indicator. It's in the polar format. So receiver power controls intensity, time controls the radius. So this line moves in this way and it will produce the spots where target is present. Now we have a scope display. It is a XY format. So receive power versus time, and time is actually calibrated in terms of distance. So this is the transmitted pulse and this is the echo pulse, the received pulse from the target. So by measuring this time gap, we can determine the distance. Another kind of radar display is the echogram. Sometimes it is also produces image. It is also XY format. Receive power controls intensity. X-axis is radar position, Y-axis is the time or range. Time is mapped with the distance. Now consider the basics of radar measurement, how it measures the distance. Transmitted signal propagates at speed of light through free space, where the phase velocity Vp is equal to c. C is the light velocity. So travel time from antenna to target is r by c. So if this is the transmitter, receiver is placed in the same point. We are transmitting a pulse of width, say tau. This pulse will move to the target and then it will return back to the receiver. So travel time from antenna to target, r by c, it will take the same amount of time to return target back to antenna, from target back to antenna. It is again r by c. So the total round trip time of flight is twice r by c, that is addition of these two. So at time t equal to 0, transmit sequence begins. Now a slight delay until the transmit waveform exits the antenna. It is possible. These small internal delays are constant and typically ignored. Now timing calibration can remove these internal delays from range measurement. So if we neglect that particular delay, we can say that time of flight or round trip flight is twice r by Vp or twice r by c if this medium is assumed to be vacuum. Now c is this. So using that relation r equal to c into t by tau in meter, we can closely approximate, we have some close approximation that c is nearly equal to 3 into 10 to the power 8 meter per second, which corresponds to about 1 nanosecond per foot one way. So this is how we can measure the range. This is the basic principle of measurement of range for pulse radar. So if we relate the range with time of flight, so if the range is 2 meter, time of flight is 13 nanometer. If the range is nearly 29 meter, that time of flight, this range is nothing but same as the basketball court length. It is 193 nanosecond. So in this way we can map it like 384,400 kilometer. If this is the range, then the round trip time will be 2.56 seconds. It is the mean orbit of the moon. So in this way you can map, you can understand the variation of range with time of flight. Now, if the intervening medium is not free space, then we have to consider the material properties. So Vp is equal to c by root over epsilon r, where epsilon r is the refractive is the relative permittivity of that particular medium, and generally the refractive index is proportional to the square root of the dielectric constant. Epsilon r is also called the dielectric constant. So Vp is equal to c by root over epsilon r, or that is equal to c by n, where n is the refractive index. So if you consider dry snow, the permittivity, relative permittivity is 1.17, corresponding refractive index is 1.08. For ice it is 3.17 and corresponding n is 1.78. So in this way you have different materials. For water, epsilon r is nearly 81, so corresponding refractive index is almost 9. So accordingly corresponding Vp will change and you have to adjust the range according to the property of the material. Now typical radars have operating frequencies between 1 MHz and terahertz band. Now question is why? The lower limit is actually determined by a host of factors like antenna size. If lambda is the wavelength, then it is wavelength is equal to Vp by the frequency, phase velocity by the frequency. Now if phase frequency is very low, then the corresponding lambda, since it is in denominator, corresponding lambda will be very high. So obviously the antenna size is of the order of lambda. So if lambda becomes very large, the antenna size would be enormous. So ultimately this antenna size restricts the use of frequency. Then ionosphere is another issue. Acts as variable RF reflector below about 30 megahertz. In the resolution of the radar's range resolution is inversely related to the signal bandwidth. So large bandwidth, maybe of the order of hundreds of megahertz, may be required for some applications and are not achievable with lower frequency systems. And ultimately, the noise. This is the relationship between frequency and wavelength. So 30 gigahertz means 1 centimeter wavelength, 11.8 gigahertz means nearly 1 inch, 10 gigahertz means 3 centimeter. So in this way, for 60 hertz, the corresponding wavelength is 5000 kilometer almost. 186 kilohertz means 1 mile or 1.6 kilometer almost. So in this way, you have variation of frequency and wavelength. And as you can see, if for the lower frequency range, corresponding wavelength is enormous. So if this is the antenna size, then it is impossible for us to build this type of antenna. Now external noise sources, different noise are there. First of all, extraterrestrial noise coming from maybe from cosmos, then galaxies, then stars, planets, all of them produces noise. Then we have atmospheric noise, mostly coming from the lightning discharge, also varies with geography, season, time of day, etc., etc. Then we have man-made noise. These are incoherent noises. They are coming from generally machinery, ignition and switching devices, power generation, distribution, and there are certain kind of coherent sources like computer, other digital systems, RF transmissions, etc., etc. We have some radar frequencies. These are the generally accepted radar frequency designations. L band frequency range is 1 to 2 gigahertz, S band 2 to 4, C band 4 to 8, X band 8 to 12, KU band 12 to 18, K band 18 to 27, KA band 27 to 40, V band 40 to 75, W band 75 to 110 gigahertz. So these are the standard band designation for use for radar, and all these bands are not useful for every kind of radar. Depending on the kind of radar or type of radar, type of target that we are going to detect, we have to select proper band of frequency. So that's all for today. Thank you.